When is it time to quit a visual search? If you're searching for something like the milk in the refrigerator, the answer is pretty clear. When you find the milk, it's time to quit. That's easy. Suppose, on the other hand, the milk is not there. How long do you want to search in the refrigerator before you decide that the milk really isn't there and you will need to go to the store to look for the milk? Or suppose that you are looking through the refrigerator for the food that you need to throw out because it's gone bad. You don't know. In the case of the milk, there was just one thing that you were looking for. In the case of the bad food, you don't know how many things there are. So when are you sure that you have found enough of the bad stuff that it's time to quit? This is the problem of quitting visual search. And it turns out not to be as trivial as it might sound. So let's go back to the milk that's not there. Maybe you would say, okay, the way to find out that the milk is not there is that I will pay attention to every object in the refrigerator. And when I have looked at or paid attention to every object and found that none of them are the milk, I will quit. This would be what would be called a serial exhaustive search. We know that's not really right. You know that can't be right because you know that you would not spend a lot of time looking in the vegetable drawer for the milk, and you would not spend a lot of time trying to decide whether or not the eggs were the milk. So what you would really do would be a serial but guided search where you would guide your attention in the refrigerator to objects that might be milk, and then if you didn't find the milk, you would quit. But how do you know that you've looked at every item that might possibly be milk? One idea, an idea that was very popular, in the 1980s, and in fact was part of the version of a visual search model that I wrote called guided search back in the late 1980s. One idea was that what you did was you would mark every item in the scene that you were looking at, not really with a marker pen or something, but you would go through and you would remember, I looked at this and I looked at this and I looked at this, and now I don't need to look anymore because I have a mark on every object that might possibly be milk. We know that's not true. One of the reasons we know that's not true is because Todd Horowitz and I did an experiment back in the 1990s where we did the following. What we were doing was we had subjects looking for the letter T, and the distractor items on the screen were letter L's. So you have to imagine a screen full of a random collection of L's, and there might be one T there. It would make sense to say, okay, if there's not a T there, I will quit after I've sort of crossed out or marked every L on the screen. But what we did was we randomly juggled the position of the L's every 100 milliseconds. That's every tenth of a second. So 10 times a second, all the items are changing position completely unpredictably. So you have no possibility at all of actually marking the items that you have rejected. And you might think this would make for a horrible search task. It sort of looks like a snowstorm of L's on the screen, but it's really not difficult at all. You look around, you pay attention from item to item sort of randomly, and then you find the T. And it turns out, quite amazingly, that you are no worse at finding that T if all the items are sitting still. You're no better at finding them if they're all sitting still than you are if they're all being repositioned every 100 milliseconds. So it can't be that what you are doing is looking at and marking each item as you go along. You must be doing something else. What Todd Horowitz and I proposed was amnesic search. We claimed that people were just looking at random, really. If you can imagine from the example from your statistics course, maybe, there are a whole lot of examples that get worked in statistics courses, where you imagine looking for a black ball in a bowl full of white balls. One sensible way to find that black ball would be pull out a white ball, look at it, put it aside if it's not white. Pull out another white ball, put it aside. That's called sampling without replacement. That's what we always assumed was going on in visual search. But what really seems to be going on is what they would call in your statistics class sampling with replacement. You pick the ball, you look at it, and if it's a white ball, you throw it back into the bowl. And even though this doesn't sound like a really good idea, that seems to be what people are doing in visual search. You pick one item. If it's not the item that you were looking for, you sort of throw it back into the bowl, and you might end up paying attention to it again. Now, we claimed that there was simply no memory for where you had searched at all. A fair number of other researchers have come along since then and said, wait, that's a little too strong, that there really does seem to be memory for where you have looked a little bit. And here's why. You could imagine that you're looking for that T among L's, but one item, maybe one of those L's, is a dramatically different color. That will attract your attention. If you somehow couldn't remember that at all you would do is you'd keep going back to the same one and keep going back to the same one, and you would perseverate, which is a neuropsychological symptom in some cases of brain damage, but it's not something that you do. You don't get stuck on one salient item that's just sitting there in the scene. So you must be able to remember some things. So I think now we would claim that visual search isn't completely amnesic. You keep some track of where you've been, but you don't keep perfect track. And the way you decide when to quit is really based on something more like the amount of time you have been searching. You develop a theory, not one that you know explicitly, but you develop an implicit theory that says, if there is a T here, I should find it in this many seconds, and roughly speaking, if I don't find it in this many seconds, I'm going to quit. That kind of a model works pretty well. It works particularly well if you are getting feedback about your search, so that you know when the search is successful and when the search is not successful. So if you discover that you have missed a target in a search, the milk was really there, but you told your friends that there was no milk, and then somebody else looked and said there was milk, next time you know you should look for a little longer. In that kind of situation, it works pretty well as a model to say that you develop a theory about how much time you should search. Now, there are applied examples in the world that become much more difficult. Think about the guy at the airport who is looking for threat objects in your carry-on luggage. Basically, he is never finding anything, right? His job is almost entirely to know when to quit, because you don't want to get on an airplane if there are a lot of targets going through that checkpoint. So how does he know when to quit? One of the things that we have found, and we published work on this in about 2005, is that when you're searching for something that's very rare, your understanding of when to quit becomes somewhat corrupted. You end up deciding to quit sooner and sooner and sooner, and you miss too many targets. Now, this is sort of sensible out in the real world. If I am looking for unicorns on a city street, I shouldn't search very long because they're just not going to be there. But if my job is to find something that's very rare, then I don't want to quit too soon. I really want to look for the right amount of time. But on the other hand, If I look for too long, then the line at the airport stretches all the way down the terminal and people start yelling at you and they miss their planes and they're not happy at all. So there's a tricky balance between searching long enough and not searching long enough. It's very difficult to get people to set that balance correctly. So one of the things that people do is to try to get the computer to help out. The computer doesn't care how rare the target is. The computer will be happy to search all day and all night. The problem is that the computer can't do it perfectly, so the computer must work with a human to do this. Humans and computers do not work together perfectly on this. As one way to think about the why this is imperfect, let's think not about the airport, but where they don't really use computer detection too much, but let's think about searching for breast cancer. If you are in North America and you do 1,000 cases in a screening exam for women looking for breast cancer, there will be about 3 cancers on average. About 0.3% of the time there will be cancers. A computer can find almost all of those cancers. The problem is that the computer will also produce what's known as a false alarm or a false positive error about 10% of the time. It'll find about 90% of the cancers. It'll false alarm about 10% of the time. That sounds pretty good, except when you're looking for something very rare. So let's suppose we've got those 1,000 cases. We have 3 cancers. Let's suppose that the computer finds 3 of them. But if it's false alarming 10% of the time, it will make 100 false alarms. So it is now delivering to the radiologist a clue that is only correct 3% of the time. And if you ask yourself, how much do you like information? How much do you like advice if it's only good 3% of the time? You know, if your friends tell you, you should try this restaurant, it's got excellent food, and they're right 3 times out of 100, you're not going to listen to your friend very much. That's the problem that we currently face in getting humans to search successfully for rare targets in cooperation with the computer. We don't really know how to overcome that problem, but maybe you will think of the correct answer. It's a ripe area for further research.